everyone. So here I'm going to be doing an example about structs and arrays of structs. But before we do that, I want to go back over an example that we had done earlier about parallel arrays. So here's the parallel arrays example that I had done. I've actually updated this so that there's no more quiz 3, and instead I have a different data type here. And I've also made the array slightly longer, sort of to really highlight this parallel array effect. So the idea for parallel arrays is simply that if things are in the same corresponding elements, it means they're related. So what I've done here is I've taken each of these 4 arrays and I've drawn them over here. And if you think about what parallel arrays do, it means that if they're in the same element, then they're related. So over here in element 2, I have a student number that is 11111. This particular student scored an 8 on quiz 1, scored a 7 in quiz 2, and has a GPA of 3.5. That's because this element 2 is where those numbers are all stored. They're all stored in element 2. That means that they're all related to this one student. Similarly, this student, 54321, their scores are 9, 6, and GPA is 3.7. So we're just looking simply at where they're positioned to say that they're related. Okay, that's parallel arrays. That's how they work. So in this parallel array example, of course, I did a read followed by what is called a linear search. So this particular loop, this block of code from here to here, right, this part, this is actually an algorithm called a linear search. It's a very standard algorithm. This is the way that you write it, and of course we read in the student number, and if we look inside the array and if we find it, we print out all the information, right? Very simple little exercise. So I'm gonna take this code here and I'm going to write a different algorithm on it. So linear search is one algorithm where we're just searching from the beginning to the end. Now I want to do something slightly different. So this, I still have the same arrays, okay? And right here I've written some code to print each of these elements. And I've actually repeated the code at the bottom. But what I want to do over here is I want to modify this data so that instead of just these student numbers being in sort of like random order, I want to reorganize them so that they're ordered from smallest to biggest. Now here's the catch though. Because these arrays are in parallel, if I say shift this 11111, which is the smallest of them all, to the very beginning, I also have to shift this number, and this number also to the very beginning because they have to remain in parallel, right? I can't just, so in other words, I can't just do the following. If I move this one, I move it to the beginning, okay, I can't just, for example, swap these two and say, oh, I'm done, right? Now it's, well, that's not ordered, but let's say I can't just do that. And the reason I can't just do that is because now the 8 isn't in the right place. I would also have to take the 8 and I would have to move it to the front and move the 10 and so on, right? Like I don't want to actually do it because that's not sorting. But in order for me to move all of those green highlighted ones to the beginning, I have to move it in 4 different arrays, okay? Which is a lot of work. But let's code it anyways. Let's see what the code would look like for this. Now, there are a number of sorting algorithms out there. I'm going to show you the worst of them. I'm telling you it's the worst of them. Okay, so in your 4th semester, you're going to take a course called Data Structures and Algorithms. That's when I will show you better sorting algorithms. But this is a very easy one to understand. This one is called bubble sort. It is the worst of the worst. Don't actually write this code, okay? This is terrible, terrible code. Don't use this, ever. But as a first example, we will use it. So how do we write it? So a bubble sort algorithm is called a bubble sort algorithm because it actually bubbles the biggest array to the back. So how we do it is it's actually two loops. Actually, let me show you the animation first, and then we'll code it. So here's the bubble sort algorithm. I'm going to let this play. So what happens is if 2 numbers are not in the right order, you swap them. and you go through the entire array and you keep swapping. And you see how the 77 keeps getting bounced to the back? That's because it's bubbling its way to the back of the array. This is why it's called bubble sort. We're bubbling the biggest number towards the back. So it's going to keep doing this. Now, every single time you go through the array once, you're going to guarantee that the biggest number gets put into the back of the array. So if I keep doing this, you could the next number to do that will be 77. Let's speed this up a bit. And I'm gonna, as I do this, it's gonna keep bubbling the biggest one to the back. Okay, and that's why it's called bubble sort. Okay, so I'm gonna stop here. Oh, it's not okay. So in any case, that's the bubble sort algorithm. That's why it's called bubble sort. It's fairly easy to implement, because all you're doing is you're going through the array and you compare successive elements, and if they are not in the right order, you swap them. That's it. That's the code. And if you do it one time, it will guarantee one number is sorted. You do it for this entire length of the array times, it will guarantee the whole thing is sorted. Okay, so 2 times through the array, 2 numbers are in the right position. 3 times through the array, 3 numbers are in the right position, and so on. It's guaranteed. So let's code this. So how do we do that? Okay, so the way we code it is as follows. Now the inside, so the outside part is we have to do this whole thing for the total number of elements we have in the array. It's actually, it's not the total number, it's actually 1 less than that. So I would have to do this num students minus 1 times, okay? And each time I do it, I have to go through the entire array, but I don't have to actually go through the entire array because the last number is guaranteed to be sorted. So I could go through the entire array. Like, I mean, if I was super lazy about it, I would declare this as simply j is equal to 0, j less than num students minus num students minus 1, but it's actually minus 1 minus I, because actually it's minus, I have to be careful about how I write this, because I don't want to, because I have to look at 2 elements that are side by side, right? And I don't want to be out of bounds. So this is actually minus 2 minus I, and then j plus plus. So what I'm doing here is that as I gets bigger and bigger, this number here gets smaller and smaller. So the first time through, it's num students minus 2. Okay. Oh, actually, no, it is minus 1. I'm being a dork. Yes, because minus 1 is correct. Yeah, because I don't, yes, this is correct. This is correct. Sorry. It's all about indexing. Because what we're doing is we're going to be basically going through this array. So if I want to think about this, I'm looking at this one together, side by side, right? I have to go through. And this is essentially j. This will be j plus 1, right? So we're going to do that. Except that we're going to keep moving these things, right? So as we do this, and sorry, that's ugly. So as we move this thing along, I have to make sure that the last j plus 1 is here, because so I have to be kind of careful that j never gets to this element, because if it does, what it means is that I will be taking these over here, and j plus 1 will be out of bounds. So I just want to be kind of careful about how far I go. So this is one of those things where sometimes you just have to do a quick example in your quick example to make sure that you get the right numbers. Okay, so my num students is 5. So the last index that I would want, and look at the first iteration only. I is equal to 0, so we can kind of ignore that. So on the first iteration, I would want j to be here, right? Like that's really the last position for j. So if I am able to do that, so num students is 5, 5 minus 1 is 4. So if j is less than 4, it will run. So over here, 3 is less than 4, it will run. If I move this over here, j is equal to 4, and it won't run because 5 minus 1 is 4, so it won't run when it's in this position, which is what I want, Okay, so sort of just do a quick verification for yourself. Oftentimes when you make a mistake that where it goes really wonky, you're probably off by one in your loop indexes and things like that. You're one number off, and that one number is critical. So just sort of be careful about stuff like this. And this is a very simple process, and what we do is we're just going to check whether or not the things are in parallel, right? So, are correct side by side. So all we do is we say, okay, student number, if student number sub j is bigger than the one beside it to the right, student number sub j plus 1, then we're going to swap the two. Now, swapping two things is pretty straightforward. So we're going to do the following. We're going to declare a variable called temp. Now, one of the things in C, you can declare your variables anywhere. But in this case, I'm actually going to just declare it here because I'm not using it anywhere else. So this is a local variable. This is a temp. This is equal to student number sub j, and then student number sub j plus sub j is equal to student number sub j plus 1, followed by student number sub j plus 1 is equal to temp. And that's swapping the student numbers. Except we're not done. After we swap the student numbers, remember we have to keep everything in parallel. So we have to actually repeat this process for our quizzes. So temp is equal to quiz1 sub j, quiz1 sub j is equal to quiz1 sub j plus 1, followed by quiz1 sub j plus 1 is equal to quiz1 sub j. And, is equal to temp. My bad. See, quiz1 sub temp. So what we're doing is we're just doing a quick swap here, and then we repeat ourselves. Now I am going to use the power of the editor here to do this. So I'm going to take this and I spelled something wrong. That's great. That actually, it's great because I realized I had actually spelled this part wrong, right? So quiz 2, this one is quiz 1. Okay, and finally we also have the GPA, right? So obviously we need a different variable here because GPAs are floats. So we need a float and ftemp, which is terrible variable name. Okay, so float temp, and I'm just going to change these to GPA, and we're good. Okay, so this is what I would have to do in order to bubble sort. Now this looks kind of like long and complicated. For every single array I would have to do the swap, and this is kind of messy. Like, you have to admit, like, this is not good looking. Okay, but this is what you would have to do. Let's verify that our code actually works. Okay, so here we go. I'm going to be printing it twice. So I'm going to do one small change here. I'm going to say printf unsorted, and then I'm going to take this over here, and I'm going to just printf sorted. Don't forget the new line. And I think I forgot the new line at the top. Yeah, so let me put the new line in, and that's it. So let's see. So I don't want to do that again. GCC parallel sort. You know, there's a good chance I have a bug in here, so we'll find out. Oh, I don't. That's good. A.out, and we run it, and you can see that originally I have the unsorted, so this is just the original data, and then I have a sorted version, and you can see it's sorted. Hey, look, magic, right? All done. And they are correctly related, I think. I hope. So the first one is 11111. It's 873.5, 873.5. The 22222, they got 342.0, 342.0. So that's good. So we verified that this is working. Now we're still talking about parallel arrays, but how would this change if we were to make this into a struct? So what would happen if we were to turn this code into a series of structs as opposed to a parallel array? So I'm going to make that change. So I'm going to copy this code here. So CP parallel sort into structs struct array .c. Okay, and I'm going to open that file. So I think I had actually made like here we go, struct array. There we go. So this is still the same code. I've only made a copy of it. So how would we turn this into a struct? Well, first we're going to create a struct for students, right? So struct student. So what does every student have? So this idea is to start by creating an object that sort of says, what does every student have, right? Like, what does a student look like? Well, they have a student number, which is an int, student number. They have a quiz 1 grade. They have a quiz 2 grade. And they also have a GPA. So this is pretty much taking exactly the same data and packaging it up so that every single student has all 4 things in it. Now, once we have the struct declared, instead of declaring 4 separate arrays for our students, what I can do is I can declare one single array for each of the students. For all the students. So I'm going to say something like struct student. So remember, this is the data type of one element of the array. My class, okay, and there are 40 elements in it. And just like, so this part is essentially saying the same thing. Here's the data type, just like this is the data type. Here's the variable name. And here is where I declare an array of that variable. Now, when I do this, what does this actually get me? So what is this my class? My class is a variable. And this particular variable happens to be a big array. So I'm going to have to, scrunch it down, okay? Okay. And there's 40 elements of this array. I'm obviously not drawing 40 elements, but it's up to 40 elements. And what I'm going to do here, so my class is an array. Every single element of this array has a certain number of data members. So there's going to be one that is called student number. There is going to be one that is called student number. There's going to be one called quiz 1. There's one called quiz 2. And there's also another one called GPA, a float, right? And so these boxes are not correctly sized. I'm just drawing them. Sorry, I'm actually going to draw them again. I'm just drawing them to sort of match. So this is what we have. We have four data members within each element. Okay. So I'm going to try to copy this. And every single array element has all 4 things in it. Okay, so each element has a student number and so on. So every single one of them looks like this. Okay, I'm just shrinking it up so that it fits, and they all look like that. So this is what I have when I declare this array. Now to initialize it, okay, think about how we initialized arrays. We had a curly bracket and then we said, well, okay, here is my data, right? I would have number, comma number, just like here. So I'm going to have the same thing, except that each member is a struct. And if you recall, how we initialize a struct is we put in all of the data needed for that one element. So here what I would put is 1, 2, 3, 4, 5, followed by the marks and GPA for this one student, which would be 10, the first element of each array essentially. 10, 9, and 4.0, right? And the second student is 3, 3, 3, 3, 3, and their data is 7, 6, and 3.2. And then the third student, 1, 1, 1, 1, 1, their data is 8, 7, 3.5. I'm just reading this, by the way, I'm just reading this off of here, okay? So third element is this, third element, third element, third element, okay? And I would keep going, okay? So 2, 2, 2, 2, 2, 3, 4, and 2.0, followed by the last one, which is 5, 4, 3, 2, 1, 9, 6, and 3.7. So those are my 5 elements for, those are what's going to go into each element of the array. So this, okay, what this will do is it would put like 1, 2, 3, 4, 5 here, then 7, 8, sorry, my bad, sorry, no, 7. I'm reading it down too, so that's my bad. I should be reading across. 10, 9, 4.0. So this should be 10, this should be 9, this should be 4.0. Okay, because that's what's inside the first element. Then the next element is 3, 3, 3, 3, 3, followed by 7, 6, and 3.2. Okay, and so on, and we can fill those out, but I'm not going to bother. But essentially this is what I have. So my class is an array. Every element of the array is a student struct, and they have all of this data in it. Okay, so how does this change our code? So first of all, oh, I have an unused variable here. I should get rid of the student because I don't need it. That was from the original parallel.c program. So I have a num students here. I have an array of structs, and now what changes? So here are the changes that I would make. So first of all, I don't have 4 arrays anymore. I actually only have 1 array. So they're not going to be called student numbers. Everything is essentially an element of my class. So this would be my class. But what I would be doing, so I would be trying to access the array first. So these change to my class, and then I would have to access that element's data member. So my class sub I dot student number, for example. And similarly, for these ones, it would be, let's see, I would be taking my class of I, and it would be dot quiz 1, my class of I dot quiz 2, and finally my class of I dot GPA. Now it's a little bit more, this seems a little bit wordier, but here's the advantage. You see all of this stuff that we had to do to sort our array. We don't have to do this anymore. We don't have to separately sort the array, because this is how we would rewrite this code. So first of all, we would still be comparing student numbers. So this would be my class sub j dot student number. Okay, so that part we would still have to do the check on. My class sub j dot. Okay, so we would access the student number, we would compare them. But here's the swap. What we would do is we would declare temp struct my class. Struct student, my bad, struct student temp. So instead of declaring an integer temp, I would declare an instance of student as temp. And I would initialize it with my class sub j. I would just simply say, hey, it's the whole thing. So temp here is a class. I teach C++. we talk about classes there. So temp is an instance of the student struct, okay? And we declare temp, we assign it the entire my class sub j. Then we say my class sub j is equal to my class sub j plus 1. And then we would say my class sub j plus 1 is equal to temp. And that is all we would need to do, because each of these elements contain the whole thing. And so this swap, I only have to do it for one element. And if I wanted to add extra data members here, the sorting code over here, that's not actually going to change. Okay, so this little bit of code for sorting an array of structs, it's going to keep working. Okay, it's going to keep working even if I decided that, oh, now I needed a quiz 3 and maybe I needed, 3 assignments, 4 workshops. I would have to add the data. I would still have to, fix my printing, but this sorting function, or sorry, sorting code blurb, they're not functions, sorry, this blob of code to sort the array, it's not going to ever change, even if I add more things to it. Okay, unless I want to change like how I compare, but as long as I just want to compare by student number, this code is exactly the same. Now I'm going to prove that this works by copying this little print code blurb and putting it down here. So, and then seeing how this works, okay? So let's try this out. GCC struct array dot c. Oop, hold on. You know what I forgot? I forgot a semicolon right there. There has to be a semicolon at the end of the struct declaration. I forgot it. All right, so let's try that again. Okay, clear. Let's run it. And as you can see, using the struct array, I am able to do all my sorting. The numbers look correct. Okay, and so I have been able to do that, but with a lot simpler blurb of code to do the sorting. I don't have all of those crazy swaps. And remember that if I have more parallel arrays, that swap using for over here, that swap piece would get longer. I would have to do one swap per array, and that's a lot of swapping and very easy to make a mistake, very prone to error. Okay, so that's it, and hopefully this helps you out. That's it for the struct demo. Thanks everyone. Bye bye.